Hi everyone. I recently started to play around with Java's new vector API that is still in development, and I've run across a lot of interesting quirks and a few bugs and some really nice features, and I thought I'd kind of make a video demonstrating the entire process along the way of how to get everything working, how to test it out. So for example, here we can see I'm running in Java 17, and I have my original scalar code, which performed okay, and then I have 4 attempts at vectorizing the code, and we can see that a couple of them, A and C, turned out okay, but a couple of them also ended up being pretty bad. So in this video I'm going to explain the whole process and try to explain why some of these are problematic. So whenever I do videos on how to program stuff, I often get questions about how I set up my IDE and stuff like that. So for the first third of the video, I'm going to cover how to install Eclipse and a couple useful plugins, and I'll go over some preferences that I find particularly useful that I didn't know about when I was a beginner. And then for the middle third of the video, I'll show the actual vector API, how to test it, and in this case I'm testing it on this computer and on a Linux VM and even on a Raspberry Pi 4. So I'll show how to do all of that and also how to automate some of it to make it a little bit easier when you're iterating through code, making changes, and then wanting to run all your tests again. And then for the last third of the video, I'm going to show how to use a tool called JITWatch, which is a tool that will let you see the actual assembly generated by your code at runtime. So for example, this is one of my attempts at vectorizing the code. I called it verify checksums vector A. And we can see the Java source code here. And the JITWatch tool will also show us the Java bytecode in the middle, including information about things that were inlined. For example, we can see here that that call was inlined. And it will show us the corresponding Intel assembly instructions here, which is really useful, especially when you are developing vectorized code and you're trying to figure out if the JDK generated appropriate instructions. So let's get right into it. So as usual, I like to start my videos in a VM. There's no need for you to use a VM, but I use a VM to help ensure that I'm showing you every step along the way and not skipping things that I've already done. So this is Windows 10 with updates installed and Chrome. That's it. We'll start off by installing the Eclipse IDE. Choose Eclipse IDE for Java developers. Okay, so this is for a very old version. Go to the current version. And then yeah, Eclipse IDE for Java developers, Windows 64-bit. And then go ahead and open the archive, extract it wherever you like. I'm going to put it on the desktop. Alright, to make it easy, I'll put a shortcut on the desktop, so you can just right-click and drag the exe, create shortcut. So the first time you run it, it will ask you where you want to put the workspace, and the default location is fine, so you can have it use that and not ask you every time. And again, on the first time, it'll show a welcome screen. We can close that. It will also show a donate screen. We can close that. I like to start by checking for updates. So if you go to Help, check for updates. It looks like it's not doing anything, but if we look down in the corner, we see a progress bar, and it is checking for updates. No updates found. That's good. So there are a couple updates I like to use. One of them is just a way to apply a theme to the Eclipse IDE. It's just strictly a visual thing to help improve it. And the other one is more functional, which is a tab that will show you your launch configurations. So let's go to Help, Eclipse Marketplace, and in the search box, type in, I'm thinking it's pronounced Jeeeyul, but Jeeeyul. And so Jeeeyul's Eclipse Themes is the plugin that I use for theming Eclipse. We'll go to Confirm, Accept, Finish. And it's signed, so we need to accept the certificate, and then Trust. We can restart the Eclipse IDE. Alright, so it has not applied the theme yet, but we'll do that later. So we'll go back to the Eclipse Marketplace. If we search for Launch, the Launch Configuration View latest version is what we want. Go to Install, Finish, Install anyway, Restart. So I was looking at the release notes of the upcoming release of Eclipse, the 2021-12 release, which will be coming out next month. And it looks like they're actually going to include the launch configuration view in that release. So you may not need to install that plugin by the time you're watching this video. Anyway, let's go ahead and go through some of the preferences. So if you go to Window, Preferences, We'll start off by applying the Jeeeyul's theme plugin. So if you go to General, Appearance, change the theme to Jeeeyul's themes, go to Apply, and then Apply and Close. And so it applied the theme, but it's kind of like half broken, and that's because you have to restart Eclipse. So we'll go ahead and do that. All right, so if we go back to Preferences, go to General, Appearance, Jeeeyul's Themes. This is where you can modify the theme. You can also pick one of the presets. So you could do something like that, or something ridiculous like that. So I made a theme that is based off of this default theme, but I made it just a few changes, and I'll put a link to it in the video description, and I'm going to just import that. All right, so I just copied it into my VM here. I have put it on my desktop. So if we go back to Eclipse, go back to Preferences, so General, Appearance, Jeeeyul's Themes, Presets, you can go to Import, and we'll go to the desktop, choose the file. Now we can select it and choose Apply, or this Apply. Okay, that's weird. It applied it and then it undid it. Let's try again.
Apply.
Apply and close. There we go. There's several other tabs we can add that I find particularly useful. So if we go to Window, Show View, Other, we have a full list of them here. First one that I really find helpful is the Tasks tab. So you go to General, Tasks, Open. And this tab will show you all of the like to-do or fix me comments in your code. I find it really helpful when working on larger code bases. And I usually like to put it maybe around here. We'll add some more, so Window, Show View, Other. If you go to the Debug category, I often like to debug from within this Java perspective. I don't usually want to switch to the debugging perspective. So I'll go ahead and add the Breakpoints tab, and I'll leave it down here. I'll also add the Debug tab. This tab is where you'll have like your stack trace or your list of threads, all that information. And I usually like to put the Debug tab up here next to the outline. The Launch Configurations plugin we just installed is also available in the Debug category. So we'll open that. And I like to keep it kind of here next to tasks. So as we'll see later on, this is where we can list all of the run configurations and external tool configurations, which are particularly helpful on more complicated projects, as we'll see later on while testing out the Vector API. If you go to the Terminal category, there is the Terminal tab. And as the name implies, it lets you get to the command line. So if you click here to open a new terminal, defaults are fine. Now you have the command line, so the same as cmd.exe. So we don't currently have any projects open, but often I like to have this link with editor feature active, and that ensures that whatever text editor tab is open, it will automatically select that file in the Package Explorer, which is really convenient for larger projects. And then the only other major thing I like to do to kind of customize the user interface is there is a whole bunch of buttons here that I don't actually use, so I like to kind of declutter my toolbar. So if you go to Window, Perspective, Customize Perspective, you can edit the toolbar here. So for example, I don't need the terminal button, which is this guy, because we now have the tab down here, which I use often enough that I just keep it there all the time. I don't need the theme selector here because I don't change themes that often, so there's no need to waste space. In the launch category, I don't really use the coverage features right now, so I usually hide those. And then these last four I don't really use, so I'll uncheck all four of those. And then if we go to Apply and Close, we now see that it's much more compact. So I thought I'd also kind of go through a lot of the preferences and point out some of the ones that I wish I would have known about earlier. So if you go to Window, Preferences, the first one is, you might recall earlier when we opened up Eclipse and it looked like it was frozen, but there was a progress bar hidden here in the corner. Well, not hidden, but not obvious down in the corner. I prefer to have it not do that. I want it to pop up something and let me know. So if you uncheck Always Run in Background, that'll probably be a little bit more intuitive. If you go to General, Editors, Text Editors, when you hover over a function to look at the Java doc, there's a feature where if you move your mouse over that pop-up, it will show more information after a little bit of a delay. Well, I prefer to just get that information immediately, so I changed this to Enrich Immediately. If you go to General, Startup and Shutdown, there's a bunch of plugins that are run at startup, and a lot of them I don't particularly find useful, and you can disable them to speed things up a little bit. So I usually disable the Gradle plugin, Equinox, Language Server, and Oomph plugins. If you go to General, Workspace, by default it will show the title of the workspace here in the title bar, but if you don't use many workspaces, there's no need to clutter your title bar with that information. So I usually have it not show that information. If you go to Java, Appearance, Type Filters, by default when you use auto-completion, like control space when you're typing out code, it will hide some of the possible options. And so, for example, you don't generally want to use like the com.sun packages or the JDK packages. But in this case, we're going to be trying out the Vector API, which is still in the incubating phase, which means it's kind of hidden in the JDK package. So we actually do want recommendations from there. So we're going to uncheck the JDK type filter. If you go to Java, Debug, the default is fine, but I thought I'd point it out. So when you create a breakpoint, if that breakpoint is hit, you can configure it so it'll suspend the current thread or every thread. In other words, the entire VM. And the default is fine, but there might be some instances where you want it to suspend everything. So I thought I'd point this out. If you go to Java, Editor, Content Assist. So when you're using Content Assist, which is that, when you press Control Space and it offers proposals of how to complete what you're typing. They recently switched to, if you select one of the proposals, it will overwrite the rest of whatever your cursor is currently over. And that can be useful, but I find it often causes me more problems than it helps. So I prefer the older behavior of it will insert the proposed text, but it won't remove anything, after your cursor. So I change it to completion inserts. And then another issue I have is it will interpret the spacebar as accepting a proposal, but I prefer to have it only interpret the enter key as accepting a proposal. So I check this box right here. If you go to Run Debug Console, by default it will limit your scroll back buffer, and I prefer to have it unlimited. So that can use more memory, but if you're developing software, I find it to be worth the trade-off. I'd rather have all the information instead of perhaps missing out on something. If you go to Version Control, Git, Configuration, if you're going to use the Git functionality inside of Eclipse, you probably want to specify your name and email address because those are used when you make a commit, that kind of thing. So you can go to the User Settings tab, add entry, user.name, type in your name, and your email, which would be user.email. And those are kind of the main preferences that I wish I would have known about earlier, so I thought I'd kind of point them out as a little bit of friendly advice. So now we have Eclipse up and running, and since we're going to be using the Vector API and it's currently incubating, what that basically means is it's under very active development and there's a lot of changes going on. So it's helpful to test your code in multiple versions of Java, and in my case I want to test it in Java 16, 17, and some of the nightly builds of Java 18, which will be coming up soon. So the official open source distribution of Java is the OpenJDK project, and you can download it, here. I actually like to use the Adoptium distribution. So if you've heard of Adopt OpenJDK, that project was taken over by the Eclipse Foundation, and they renamed it Adoptium. And the reason why I like them a little bit more is because if you're on Windows, they provide installers, which we're not actually using in this particular video. But that can be nice because it will associate, a .jar file with Java, so you can double-click it to open it. And then also, the reason why I like it in this particular case is they have a little bit better support for other platforms. There's builds for 32-bit ARM, there's builds for, more architectures, more operating systems, and that kind of thing. All right, so if we go to Adoptium and go to other platforms, let's start by trying out Java 16. And we'll do Windows, 64-bit. We don't want the installer, we just want the regular zip file. Well, that's curious. Try that again. Okay, well, that time it worked. We also want to download Java 17. And I'd like to try out Java 18. And it looks like the Adoptium project is planning to have some early access builds, but they don't currently. And on the OpenJDK project, they do have early access builds, which I have tried, but I prefer to actually try some nightly builds. So there's a guy named Alexei Shipilev. I think he's one of the Oracle employees, but he has a great website and a lot of great articles too. But one of the things he does is he maintains a collection of builds. And if you go to builds.shipilev.net, the OpenJDK-JDK folder is your basic OpenJDK branch, I guess you could say. And we'll go down here to Windows, 64-bit server release. So if you're wondering what the server and release means, it's kind of explained up here. But basically, server is your normal version, and release is also the normal version of the build. All right, so we have our 3 versions of Java. I'm going to go ahead and make a folder on the desktop called Java Projects. You can call it whatever you like. And in there, I'm going to extract the versions of Java. All right, we have Java 16, Java 17, and a nightly build of Java 18. Let's now tell Eclipse about those versions of Java that are available. So if we go to Window, Preferences, Java, Install JREs. So by default, Eclipse includes the Just J distribution of Java 16. It's perfectly fine for normal use, but it seems like they don't include the incubating vector API, or if they do, it's in a different package. So it's actually kind of annoying for this particular demonstration. So let's go ahead and add the new versions of Java. So you go to Add, Standard VM, go to Directory, and just pick the root folder. You don't need to go to bin, but just the root folder. Make the name a little bit shorter. Just call it JDK16. Finish. Repeat the process for 17 and 18. All right, so now Eclipse knows about the 3 new versions of Java, and we can pick the Adoptium Java 16 version as the default by checking the box next to it. We can go to Apply and Close. So we're finally ready to start writing some Vector API code. So let's create a new project. You could click here, or you can go to File, New, Java Project. We'll give it a name. The defaults are fine. Go to Finish. Actually, I don't really want to bother making it a modular project, so we'll go to Don't Create. And we have our empty project. We can right-click, New, Class, call it Main. We'll create a main method. And instead of me typing out all the code, I'm going to go ahead and copy and paste it in, and then I'll explain kind of the basics of how it all works. So we've got all the code in right now, and we can see a whole bunch of red squiggly lines indicating errors. So if you right-click on the project and go to Properties, go to Java Build Path, Libraries, the JRE System Library, Edit. And for some reason, it's still defaulting to the Just J Java 16, and we want to use the Adoptium Java 16. So go to Alternate JRE, JDK 16, Finish, Apply and Close, and now all those red errors go away. Now I'll briefly explain what this code does. So if you are familiar with my videos, you might have seen Telemetry Viewer, which is a tool that I wrote for visualizing data. And one of the bottlenecks is in obviously processing the packets of data. And part of that is verifying the checksums if you're doing a binary packet. So I thought I would write this quick test to see if I can speed up checksum validation. So as an example, here is what a binary packet might look like in Telemetry Viewer. In particular, if you do the stress test mode, this is kind of what it would be generating. The first byte is a sync word, which is just a constant that I use to help ensure that I'm aligned with the beginning of the packet. The following 8 bytes are, I guess you could call it the payload region. It's the actual data, the telemetry. And then the last 2 bytes are a 2-byte checksum. And so in particular, in the payload region, I'm sending 4 16-bit signed integers, and they are little endian. So in other words, they are little endian shorts, if you want to use Java's terminology. And so because it's little endian, that would be equivalent to hex 0201, hex 0403, 0605, 0807. And then finally we have the checksum, which is also little endian, so it would be hex 1410. So what I start out by doing is I create a buffer to hold a bunch of generated packets. And just from testing, I found that using approximately 3 million packets was a good number that would give me consistent results when testing. And so, of course, powers of 2 are important, so it's more like 3 mega packets, not 3 million, but you get the idea. So I go through that buffer and I populate it with 3 mega packets, and they're all the same values. When I run the code, just to make it easier for myself, I have it print out a bunch of information about the current computer, so the host name, information about the version of Java, information about the OS, and information about where Java is located. And I just do that because I'm going to be running this on Windows, I'm going to be running it on Linux in a VM, I'm going to be running it on a Raspberry Pi 4, so I'll have a bunch of runs that I want to look at, and I'd like to verify that I'm looking at the right run when I'm trying to judge performance. And then I start benchmarking the code. So a popular tool for benchmarking in Java is JMH, but I decided to keep it simple. And as we'll see later, even though I didn't use JMH, I was able to verify that my code is actually running correctly. In other words, it's not being optimized out or anything like that. So I'm doing a very simple benchmark where I just record times. So I have a start timestamp. I call a function, and I do it 500 times just to make sure that the just-in-time compiler has enough time to kick in and actually optimize things. And then I record the end timestamp, and I do the math, and I print out some data. And so I repeat that test for a version of checksum validation that uses scalar code, in other words, my original code. I also have 4 different attempts at vectorizing the code. So I called it vector A, vector B, vector C, and vector D. And that's just my very first attempts at vectorizing code. So this is not going to be a video about expert crafting vectorized code. This is kind of showing some of the problems I found along the way, some bugs, and some problems in my code. And so let's take a quick look at the code. The original code, the scalar code, is relatively simple. I don't bother with checking byte 0, which is that sync word, because for this example, I'm just testing checksums. So I start by looking at the payload region, which is bytes 1 through 8. I interpret them as 4 signed 16-bit little endian integers. I add them all up into an accumulator. And then I also look at the last 2 bytes, bytes 9 and 10, which are the reported checksum. I interpret that also as a 16-bit signed little endian integer. And I check to see if that number is equal to the accumulated sum of the payload region. If they're different, then I know that I have a checksum error, and I print out to the console. And so here we extract the first short from the payload, the second short, third short, fourth short, and it's all put into the accumulator. And I only want to look at the lower 16 bits of the accumulator. And then here I extract the reported checksum as a short, and I compare it. If they're not equal, then we have an invalid packet. So my first attempt at vectorizing the code was perhaps the most simple, most crude way of doing it. And I realized that let's see. If you look at this packet, the payload region, which is 8 bytes long. 8 bytes is 64 bits, and 64 bits is a common SIMD register size. So what I do is I basically copy those 64 bits, those 8 bytes, into a SIMD register. And in this case, I have to tell it that it's a little endian. And then I use a reduction operation to add up all the lanes of that register. And that will give me the actual sum. And then using some scalar code, I extract the reported sum, and I compare it like before. And this code performed a little bit better, but just a little bit better. And so one of the things I thought I would try is using a wider register. So most modern computers these days have 256-bit SIMD registers. In fact, I think these days 512-bit is actually very common. So I thought I would try processing 3 packets at a time. So what I do is I put 3 packets into one of these registers, and then because I only want to look at the payload regions, I need to extract the reported checksum and the sync word that is between the 3 packets. And so I used masks for that. So here I populate a register with the, the 32 bytes of data. And here is how I basically remove the undesired checksum and sync words between the 2 packets. And then because that was how done with bytes, because the sync word is not a short, it's just a byte, so I have to do it manually. Now we're left with a bunch of shorts, but we need to reinterpret them as shorts, so I do that here. And then now we have the 3 packets in one register, and I use a reduction operation with a mask to get the sum of the first packet and the second packet and the third packet. And then with some scalar code, I extract the reported sum of the first packet, second packet, and third packet, and I compare them like before. This code ended up being very, very slow. We'll see why later on. So before I was using masks, and I thought I would try using shuffles instead, because after reading through the Java doc, that actually looked like a better way of doing it, a more efficient way of doing it. And what a shuffle is, you can basically shuffle the bytes in the SIMD register. So you can tell it the index of each byte what you want it to be. So I want byte 0 to be byte 0, and byte 1 to be byte 1, blah, blah, blah. But then the 8th byte, I want it to actually be byte 11. In other words, I'm getting rid of the checksum and sync word at the end of the first packet. Repeating on here, so I then want the, let's see, this would be 15. I want byte 16 to actually be byte 22, which is the start of the payload region of the third packet. And then I have the rest of the third packet. And because you have to tell it all 32 bytes, I just have it repeat byte 0 for the last 8 bytes in the register. And so here I am, I populate the register with 32 bytes. I then use that shuffle to rearrange the bytes inside the register. And then because I don't actually want these 8 last bytes, I want to zero them out. I use a blend operation to write them all to 0. And then like before, I interpret that as shorts. And as an optimization, I thought I would try to test all 3 packets at the same time. Now, this is not a good way of doing it because it won't catch all checksum failures, but this was a quick test to see if this was even a viable idea. And so here I am, I get the sum of all 3 packets as a single sum. With some scalar code, I interpret or I extract the reported checksums of all 3 packets, and I add those all together because I got the sum of all 3 together. And I compare them, and if they don't match, then I know that I have at least one corrupt packet, and I report that. This code worked, but it was not very performant either. It was kind of slow. So reading through more of the Java doc for the Vector API, I found what looked like a perfect solution, which was when you actually when you actually populate a vector, you can give it an array of offsets, which is what I'm doing here. So in this case, I'm filling the SIMD register with 32 bytes of data. The data is coming from the buffer array. The data starts at an offset. And then instead of just copying 32 bytes immediately from that offset, I tell it that I want it to be from these offsets relative to the original offset. So in other words, byte 0 of this SIMD register will be at offset 1. Byte 1 will be at offset 2, and so on and so on. So this is basically a more efficient way than shuffling the data like I did in the previous attempt. And also I get the benefit of I can fit 4 packets into the register instead of 3. This gives me a byte vector register, and I want to interpret it as shorts. And then again, as a quick test to see if this is a viable idea, I calculate the sum of all 4 packets at the same time. And then I extract the reported checksums of all 4 packets, and again I compare them, and if they're different, I know that at least one of those 4 packets is corrupt. This ended up being kind of slow as well, and I think that's simply because it isn't implemented yet in the Vector API, but I'm not 100% sure. So these are literally the first 4 ideas I had for vectorizing the code. They're not the best way of doing it, but I thought I would share what I've got because I found a lot of bugs along the way and some weird performance issues that I found particularly surprising that I think others might benefit from knowing about. Let's run the code now and see how it performs. So normally you can click the play button and it would just run, but we need to add a flag to the JRE. So if you click on the drop down and go to Run Configurations, choose Java Application, New Launch Configuration. We're going to have several launch configurations, so let's actually give it a useful name. So I'm going to be running the code on this computer and on a Linux VM and on a Raspberry Pi. So I'm going to indicate that this run configuration is going to run on this computer, and it's going to run with Java 16. If we go to the Arguments tab, we need to pass a VM argument. The Vector API is still incubating, which means it is not done, it's not ready for production code, which means it is not enabled by default. So we have to manually enable it at runtime. So you need to use the add modules JDK incubator vector flag. And then let's pick the JRE. So I think it did default to the appropriate Adoptium Java 16, but just to make it really obvious, let's go to alternate JRE, and yeah, that is the Adoptium Java 16. We can click Apply. Let's also duplicate this and set it up for Java 17 and Java 18. So after we click Apply, we can click on the Run Configuration and then go to Duplicate. We'll rename this for Java 17 and then pick Java 17, go to Apply, and again, click on the Run Configuration, Duplicate. All right, so there we have it, 3 different run configurations. We can go to Close, and here in the Launch Configurations tab, we can expand here, and we have our 3 run configurations. So this is part of why I like the Launch Configurations plugin, is when you have several configurations, it's more convenient to just double-click on one. Without this, you'd have to go to the drop-down and then Run Configurations and then double-click it here. It's just slightly more convenient. Anyway, let's go ahead and run it with Java 16. So if we double-click, and we always want to save, well, that looks horrible. One thing I should point out, though, is this is actually a bug in Java 16 when running in a VM. So these two are ridiculously slow, but only when run in a VM and only in Java 16. Let's try it out in Java 17. So this is kind of what I expected. The scalar code is performing reasonably well, I guess. My first attempt at vectorizing it is a little bit better, but not by a whole lot. My second attempt, vector B, is surprisingly very slow. So let's take a look at that and see why. So vector B, I think perhaps the biggest difference is this one uses masks. And if we look at the JEPs for the Vector API, okay, that's a weird thing with This VM, I don't know what's going on there. Anyway, okay, so ignore that visual problem here in Chrome. But if we look at the various JEPs, so JEP 338 is the vector API as it was put into Java 16. 414 is the vector API as put into Java 17. And 417 is targeted for Java 18. In other words, it's not done yet, but hopefully it will be. And looking at JEP 417, I see here some curious information. So they're planning to improve performance of vector operations that accept masks. So in other words, the code that I wrote which uses masks is probably not fully optimized, and that could explain why there's a very significant performance loss. So I'm curious to see if that will perform better after Java 18 is released. Vector C performs a little bit better, and that's kind of in line with what I expected, because if we look again at the code, this is the one where I calculate the checksum of all three packets at the same time, which is not good enough for production, but it was just a quick test. And we can see that that did help out a little bit. Now my fourth attempt, vector D, it turned out surprisingly bad. I have a feeling it's because it's not properly optimized yet, but it's also entirely possible that maybe it can't, because with SIMD instructions or vector instructions, ideally you want all your data to be properly aligned. So at the very least you want it to be word aligned, but ideally you'd want it to be cache line aligned. And as we can see here with all my offsets, almost nothing is aligned. And that's because the packet was not designed with vector instructions in mind. So let's see if it performs any differently on the Java 18 nightly build. All right, so unfortunately the vector D code is not really any different in the Java 18 nightly build. So Java 18 is not released yet, and I'm curious to see if the JEP 417 code has been merged into the OpenJDK code. So if we go to OpenJDK on GitHub, yeah, I don't know what's going on here. This is some weird issue in Chrome has that problem. Anyway, so if we go to the JDK repo, we go to pull requests. In my notes, I think it was pull request 5873. Yeah, so integration of JEP 417. It is still open. In other words, this code, which will hopefully improve performance of masked operations, is not yet in the OpenJDK 18 nightly builds. So I'm going to be keeping an eye on this to see when it gets merged in, and then I'll be eagerly trying out another nightly build from Shipilev's website and see if it performs any better. So having only run on one architecture and one operating system so far, we can already tell a few things. So I don't know if you remember the performance numbers from earlier, but the vector A code has been steadily getting a little bit faster. Before it was about 10% faster in Java 16, and by Java 18 it's about 17% faster. And there were other similar small improvements to the other attempts at vectorizing the code. Well, my Telemetry Viewer project, which is what is going to be using this vectorized code if I can get it to perform nicely and reliably, it runs on pretty much everything. So it runs on Windows and Linux and hopefully Mac OS. I need to see if I can get a Mac OS laptop to test it on. But in theory, it should work on Mac OS. It works on a Raspberry Pi. So I'd like to make sure that everything works correctly on all of those platforms. So I don't have a Linux computer sitting around, but I can run a Linux VM. So let's try that. All right, so here's my Linux VM, and then let's see if we can get a system monitor up and running. All right, yeah, so this way we can take a look and see it at CPU load when it's actually running the Java code. So I'm going to leave this VM running. We'll go back to Windows 10. And I'm going to basically copy my code to the Ubuntu VM and run it with SCP and SSH. So let me go ahead and I'm going to copy my encryption keys to the desktop. I hope it's obvious you should not be storing your encryption keys on the desktop, but again, this is a video tutorial, so I'm going to keep it simple. If we go to the Terminal tab, we can use Secure Shell. All right, so SSH, the username, the host name, And then because I'm using key encryption, use -I and then the path to your RSA private key. So this is the first time I'm connecting to that VM from within this Windows VM. So I'm going to accept that fingerprint. And here we are. I'm logged into the Ubuntu VM from within Eclipse. So I'm currently in my home directory, and because before this video I was trying things out, I already have a Java projects folder, but I'm going to remove that. So we can start over fresh. Now, similar to Windows, I'm going to create a Java projects folder. We'll go into that folder, and let's go ahead and download Java 16, Java 17, and a Java 18 nightly build. So again, we'll go to Adoptium, Other Platforms, Java 16, Linux, 64-bit, Intel, copy that, and we can use wget, and then we can paste the link. So if you're not familiar with a lot of terminals, you can't usually use Control-C or Control-V. So if you right-click, you can see here we have to use Shift-Insert to paste, or you can, right-click and paste. And press Enter. Okay, we also want Java 17. All right, so there we have Java 16, 17, and a nightly build. Let's go ahead and extract the archives. So you can use tar and then -xvf to extract and then have it be verbose. In other words, print out all of the files it creates. All right, so just like in Windows, we now have our 3 folders. We have the Java 17, 16, and 18 nightly folders. So we're going to eventually set up a tool in Eclipse so that we can run it from here. But to show how it all works, I'm going to do it from the terminal. And basically, this is a very simple program, or a very simple project. It's only one file. So we can use scp to copy the main.java file to the Linux VM. All right, so we're using scp, which is secure copy. I'm using keys, so we have -I and then the path to the private key. We then have the source file, which is the main.java file. And we created our Eclipse workspace in the default location, which will be in C, users, your username, and then Eclipse-workspace. Then you have the project name, the source folder, and main.java, which is that and that. And the destination is username, host name, and then in the home folder, I have the Java projects subfolder or subdirectory. So press Enter. All right, so I should probably provide the, oh, actually, okay, I see the problem. I am currently logged into the Ubuntu VM. I meant to do this just from DOS. Let's see. Go ahead and copy that. I'm going to exit out of the secure shell connection. Now we're back in DOS. I'm going to go ahead and paste that command again, and now it should work. And in this case, I'm using a relative path for the key, and this is relative to my current location. So that should be fine. There we go. So now it copied it. We can see there's the file name, 100% done, and that was the size and speed. Now we need to use Secure Shell to actually run that code on the Linux VM. All right, so it's a similar command. We're using Secure Shell. Again, I'm using the keys, so there's the path to my private key, username, host name, and then this is the command we want to run. So this entire thing is the command. I'm using the path to the Java executable. So in my home directory, I have the Java project subfolder, and then I have the JDK16 folder. We can see that up here as well. In there's the bin folder, which has the actual Java executable. And then because the Vector API is incubating, we need to enable it at runtime. So we have the add modules JDK incubator vector flag. And then we give it the path to the source code, which is in the home directory. We have the Java project subfolder and then main.java. In recent versions of Java, if it's a single file, you can just run it with Java. You don't need to use Java C. So press enter, and we can see here that it's going to start to run. So I'm going to go ahead and terminate this with Control C, because we're going to go ahead and do this from within Eclipse. But it also brings up another important thing I want to highlight. If we look at the Ubuntu VM, it's still running the code. We can see that CPU 1 or core 1 is still at full load because it's executing the code. If you terminate something from Secure Shell, or if it's running within Eclipse as a run configuration later on, as we'll see, it will abort the, I guess you could say, the command line, but the code is still going to run. So what we can do is we can Secure Shell into the VM. So now I'm logged back into the Linux VM, and we can kill the Java program. So kill all -9 Java. And now Java is actually stopped. And we can see here CPU load drops back down to 0. So it's just something minor, something to keep in mind. If you ever terminate something or if a connection gets lost, it's possible the code is still running on your VM or remote device if it's an actual device. So I'm going to open up Notepad just so we can easily copy and paste things. Let's scroll back up to the, there we go. Let's copy the scp command. Again, you can't use Control C. We have to right click and copy, or Control Insert. Paste that into Notepad. And similarly for the Secure Shell command, paste that into Notepad. Okay, so for run configurations, which you can do from here, or you can do run configurations, that would work for a Java program running locally. But there's another feature which is an external tools configuration. And if you go to Program and then create a new one, this will let us invoke an external tool. In this case, we're going to use the command line as an external tool. So this is a really useful way to have Eclipse run something for you outside of Eclipse. We're going to give it a name similar to the other ones. So in this case, it'll be a Linux VM running Java 16. For the location, we want to pick the cmd.exe program. In other words, your DOS shell. So we can go to Browse File System. It'll be under C, Windows, System 32. cmd.exe. So I'm just typing on the keyboard. Like if you didn't know, you can just type in a letter. So like if you type in, oops. So like to get to System 32, if I just type in SY, it'll jump there. That's what I was doing earlier. It's CMD. Anyway, so click cmd.exe. For the working directory, we don't really care about that. It doesn't matter in this case. For the arguments, we can do /c to execute the following commands. We can go ahead and copy and paste the scp command. And then we want to also run the ssh command. So we can do space and space, and then copy and paste the Secure Shell command. And that's really all there is to it. So we can click Apply. And let's, like before, we'll duplicate this and do one for Java 17 and Java 18. So I clicked Apply, make sure that the external tool configuration is selected, and then duplicate. Okay, I don't remember the path here. Let's save that for now. Scroll up. There we go. Now we can go back. We'll go to Run, External Tools Configuration. We'll go back here, and now I can edit this to match here. Click Apply to save that change. Again, we'll duplicate it. All right, so Apply, and we now have our 3 external tool configurations. We can click Close, and then here in the Launch Configurations tab, we can expand the program category, and we see they're now here. So let's go back to the console. Let's remove everything. And if we double click it, we can run it and see how it performs. So here we have an error of it could not find my private key. And that's because if we go back to run, external tools configuration, I provided a relative path, and of course I didn't set the working directory. So let's go ahead and just make it an absolute path. And we need to edit that for both the scp command and the ssh command. Apply that to save, and then edit the other two run configurations. All right, we can close out of that, and let's try again. There we go. Now it was able to log in, and it's running the code. Like before, again in Java 16, there's an issue where in a VM, it's really, really slow for the code that I wrote for vector B and vector C. And that was fixed in Java 17. So anyway, let's let it run and see what happens. And yeah, like before, we can see there's a severe performance issue in Java 16. Let's try Java 17. Well, that's better. That's more in line with what we saw in Windows. And let's try the Java 18 nightly. All right, so yeah, nothing really major here. It's similar to what we're seeing in Windows. Again, the goal of this was not to compare Windows versus Linux because they're both in VMs and the VMs are not set up identically. I just wanted to verify that there weren't any severe performance issues or bugs in one or the other. So now I'd like to try it on the Raspberry Pi 4. And like before with the Linux VM, I use Secure Shell, and I've changed the default user from Pi to F in my case. All right, and this is the first time logging in on this VM, so I need to approve that fingerprint. And here we are. So again, just like before, we're using Secure Shell with key. There's the username, and there is the host name. So by default, you probably have Pi at Raspberry Pi, but again, I changed my username and host name. So I did some testing earlier, so I'm going to go ahead and remove that stuff. And just like with the Linux VM, I'm going to go ahead and create the Java projects folder and then download the JDKs into it. So we go to Adoptium again, and we're going to go to Other Platforms, Java 16, Linux. Now I'm using Raspberry Pi OS, and it's actually a 32-bit distribution by default. So we're going to try it out on the ARM32 architecture. Go ahead and copy that. Now we'll get Java 17. So here it'll be the ARM32 HFLT server release package. All right, so there we are, very similar to the Linux VM earlier. We have our Java 18 nightly, Java 16, and Java 17 all extracted. Let's go ahead and create some more external tool configurations. So you go to Run, External Tool Configurations. We can just duplicate one of these, so we'll select it, duplicate. All right, so all I needed to change was I changed the name to Pi 4, and then I changed the host names to match my Raspberry Pi. So in my case, it's F-Pi 4. Use whatever it is that you're using. The default host name is Raspberry Pi. Anyway, so we click Apply, and we can go ahead and duplicate the Java 17 and 18 as well. Alright, so yeah, they're all identical. You just change the host names and the name of the actual run configuration. So we can go to close, and we can see they're now here. Let's go ahead and try it on Java 16. So we can see the code is running on the computer. And also we can see it running on the Pi by looking at the CPU load and CPU temperature graphs. Well, that was great. So it looks like Java crashed when it tried the vector B attempt, and we got a should not reach here, so that's good. We can also see that when it did run the vector A code, it was incredibly slow. If we take a look at the vector API JEPs, we can see that for now at least, they're only targeting the Intel 64-bit and ARM 64-bit architectures. And the Raspberry Pi OS, like I mentioned earlier, is currently a 32-bit OS. So I actually did not expect this to perform very well, but it is kind of disappointing to see that it actually crashed the runtime. Anyway, let's see if Java 17 is any better. Alright, this has been running for a very long time. I'm going to just stop the run. In the past, I've done this without recording, and I've had two different things happen. One time I had the runtime crash, similar to with Java 16, and the other time I had Eclipse crash, and that was letting it run overnight, and so it's probably running for 5 or 10 hours. Anyway, let's stop this and then try the Java 18. So I'm going to stop the run, and again, we'll use Secure Shell to terminate Java on the Raspberry Pi. Now I'm also going to try a 64-bit version of Raspberry Pi OS. So if you go here, and again, this will be a link in the blog post that I'll have in the video description. But if you go here, you can download a 64-bit beta version of Raspberry Pi OS. I'm actually using the earlier version. There's a new version that came out just a couple days ago, and I haven't tried it yet, but I don't think it'll have any significant performance differences. Actually, I just realized I was jumping ahead of myself, so we didn't try Java 18 nightly. I'm going to run it again on the 64-bit OS, and it'll have the same effect, but just so you know, the Java 18 nightly from the Shipilev builds website does not run. You get a glibc error because it was compiled against a newer version than what is included with Raspberry Pi OS, but we'll see that later. Anyway, I've got my Raspberry Pi. Now it has an SD card for the 64-bit beta version of Raspberry Pi OS. If I try to Secure Shell into it, I'll first get a warning because the Secure Shell fingerprint has changed. The host name is the same, but because it's different software on the Pi, it's going to think that we're, being man-in-the-middled or whatever and having somebody trying to eavesdrop on the connection. So that's what happens. And what we can do is we can edit the known hosts file. In my case, I'm just going to delete the file because I'm running in a VM and there's no other important hosts that are memorized. Okay, that's really annoying. Alright, let's just try Notepad. There we go. I'm just going to go ahead and delete that last line. We'll save that, close, and now we can try Secure Shell again. We'll confirm the fingerprint is fine. Alright, so now we're finally logged back into the Pi. And again, because I was testing things out before the video, I have a Java projects folder. I'm going to go ahead and remove that. And like before, let's create the Java projects folder, download the 3 different JDKs, and extract them. So we'll do Java 16, Linux. This time we'll do AArch64, which is ARM architecture, 64-bit. So it looks like there's something weird going on here with Secure Shell. I pressed enter and I can see on the CPU monitor on my Pi it's actually doing some work, so I think it's extracting the archive. But for some reason, this isn't really updating. Okay, there. Okay, now it's starting to. All right, so that finally finished. It was really slow, but in any case, yeah, it extracted fine. And we can see we now have Java 16, Java 17, and the Java 18 nightly extracted. So all of the commands are exactly the same as before, so we can reuse the existing external tool configurations. So let's try running Java 16. Now the Java 16 test has finished running, and we can see that it is still very, very slow, pretty much unusable in many cases. And looking into it, I think I realized why the majority of them are very slow on the ARM, even much more so than on Intel. And that is, on an Intel processor, it can easily handle a 256-bit register. But on most ARM processors and the one in the Raspberry Pi 4, they have 128-bit registers. So we can see here that on the Raspberry Pi 4, they're using the ARM Cortex A72. So I'm trying to see where I found. I remember researching a while ago, and on the A72 used in the Pi 4, it was saying that they are 128-bit wide registers, and it's not showing here, but it looks like on similar architectures, it's definitely 128 bits wide. So that appears to be a large reason for why the code that I wrote that is using 256-bit registers is very painfully slow. So one of the things I'm going to try is 128-bit registers. And more importantly, if you read the Java doc for the vector API. All right, so here we have the Java doc for the vector package. And we can see here that they recommend and show to use the species preferred way of doing things, which would be a better way of doing it. That way it's really more cross-platform and, well, cross-architecture, I should say. So I'll probably be trying that out in one of my next attempts at vectorizing the code. So I could run the Java 17 test again, but I've done it before, and it's fairly similar to this. Maybe 5 or 10% faster in a few things, but overall it's identical. If we run with Java 18, we'll get this error, which is the error you would have seen if I tested it on the 32-bit version of Raspberry Pi OS. And it's simply because the build from Shipilev's website requires a newer version of glibc than is included with Raspberry Pi OS. If you go to the OpenJDK website, you can download, let's see, if you go to Early Access JDK 18, you can download the Linux AArch64 build here, and that will actually run. Unfortunately, the performance is, again, it's fairly similar. It's maybe a few percentage points faster, but that's about it. So I'm not going to bother demonstrating that, but it's there if you want to try it out. So on a complicated project, you'd probably set up a CI/CD pipeline to automate all this, because it'd get really annoying to make one change and then having to double click on each of these 9 run configurations. Well, to keep this simple, Eclipse has a launch group feature, which can simplify this quite a bit. So what we can do is we can go to run configurations, and instead of a Java application, you can go down to launch group, create a new one. Let's give it a name. I'm going to call it run all, and then we can add either a launch configuration or an external tool configuration. So I'm going to have it first run the Java 16 test on this computer, and the launch mode is fine. You can leave that at the default of inherit. And for the post-launch action, you can have it so that Eclipse will run all of these in parallel or in series, and because I'm testing performance, I want them to be executed in series. So I'm going to tell it to wait until terminated, and then go to OK, and we'll go ahead and keep adding more and more. All right, so here we have a launch group, and basically it will run all 9 of our tests, and it'll do them in sequence. And so it's pretty obvious that performance in Java 16 is not that good, so I would probably disable or not even include the Java 16 versions, but you get the idea of this is how you could automate your testing. And so you can click Apply, and then Close, and then here we have it in the launch group category. So I'm going to go ahead and close all of the consoles and then double click this. So it's starting off with the first one, which is on this computer running Java 16. And this is going to be a long test. So I'm going to let this run and record, and we'll take a time lapse and see what happens at the end. So I let it run overnight, and here we can see the results. So in the debug tab, we have all of the runs, and then more importantly, if you go down to the console, if you click on the display selected console, you can see all 9. So for example, we'll look at the first one, compare that with Java 17, which obviously fixed the VM problems. Java 18 so far has almost no change, but again, that's because we're waiting for that pull request to get merged into OpenJDK. On Linux, again, we see that VM problem, and then it clears up, and it's a little bit faster with Java 18. And again, on the Pi 4, we see the same issues as before. So that's a simple way to kind of automate testing. Now again, of course, like I mentioned before, I probably wouldn't bother testing Java 16 anymore, and I might not test Java 18 until that pull request is merged in. But you get the idea, and you can of course edit that, so you can edit your launch group and disable whichever ones you don't really care about. So the last part of this video, I'd like to cover JITWatch, which is a tool for looking at how your Java source code gets converted into Java bytecode, and then finally how it gets converted into assembly, like the actual instructions running on your CPU. So to do that, we need to add a couple more flags to the runtime. So let's go ahead and duplicate one of our run configurations. So if we go to run configurations, let's do Java 17. We'll duplicate that. So I added the text collect JITWatch log to make it obvious what we're doing, and then we go to the arguments tab, and we need to add several more arguments. Alright, so the first flag is required just to enable the rest of it. These two flags are used to log the compilation details both to the console and to a log file. This is optional, but what it does is it has the assembly printed in the Intel style, which I find helpful because if you're looking through the Intel documentation, it's a little bit easier to understand if you do it that way. And finally, we have another option which is optional, which will let you specify the file name of the log file. And that way, when I run JITWatch, the default, which will be the previous log file, will be correct. So it just makes my life a little bit easier. So we can go to Apply, and we can go ahead and run it, and we'll see one of the issues. Looks like I have a typo in there somewhere. Let's see. There shouldn't be a plus sign here. So in case it isn't obvious, the plus signs are used to enable a feature, and you can also have a minus sign to disable it. But in this case, it's not so much enabling a feature as configuring it. So that's why you don't need a plus sign here, and you don't need a plus sign here. So we'll save that. Try it again. There we go. So I'm going to go ahead and stop it because I want to show you something. So this is the disassembly of the code. And the problem we have is right now it's printing out machine code. In other words, the hex bytes. It's not actually disassembling it because the JRE needs a library to actually convert that into the Intel assembly instructions. And for licensing reasons, they're not able to include that library with the JRE or the JDK. So we need to compile it. I was able to find that library pre-compiled for 32-bit Windows and for Linux, but I could not find it for 64-bit Windows. So I'm going to show you how to compile it yourself, and then we'll see how to get the actual assembly instructions. The first thing we need to do is install Cygwin. You can download the installer here. Alright, so now we need to pick the packages we want to install, and there are 4 different packages that we need. So if you expand the all category, go down to Devil, expand that. We want GCC Core. So if you click on the drop down, we can install the latest version. We want Make. And again, we can click the drop down, choose the latest version. We want the MinGW64 version of GCC code. GCC Core. So make sure you do MinGW64, x86-64 GCC Core. And then finally, just to make it a little bit easier, let's install wget. That will be in the web category, wget. So now we can go to Next, Next. All right, and the default options are fine, so we can go to Finish. Let's open the Cygwin terminal, and we'll go to the desktop. First thing we need to do is download binutils. So off camera I tried 2.37, but I had problems with it compiling. It would fail during the make process. But 2.36.1 worked just fine for me, so I recommend you try that. We're going to go ahead and copy that link, and wget, shift insert to paste. And then we need the source code for the JDK. So we'll go to Releases, Tags. I don't think it really matters, but I'm going to go with 17 general availability. And we'll download the code. All right, we can see we have the 2 archives here on the desktop. Let's extract them. Just like before, tar-xvf. The tool we need to build is called HSDIS, and if we go into the JDK folder, then the source folder, utils folder, and finally HSDIS. And now we need to build this tool, so we can use make. Alright, so there's the long command. We're calling make. We're telling it the OS is Linux, so obviously we're in Windows, but that's fine. It'll work just perfectly. We need to tell it which MinGW to use, and then the path to the binutils source code. And there needs to be, 4 layers of traversing up the path. So press enter. And this will take a little while, but then at the end we should have the DLL that we need. Very good, it finished compiling, no errors. So now we need to copy the DLL into the various JREs. So that's the DLL, and we need to put it in the bin folder of each of the JREs, or I guess JDKs. So we go up 4 levels. Now we're back at the desktop. Java projects, JDK 16, bin. Repeat that for 17 and for 18. All right, now we're done. We can exit. We no longer need the code for the JDK or binutils. We can delete those. If we go back to Eclipse and try this again, I'll go ahead and stop it, but now we can see we have the actual disassembly. So now we need the actual JITWatch tool. Download the Windows version. Alright, and I want to go ahead and put this jar file inside the Eclipse project. So I'm going to go ahead and copy that. Right click and paste. If we go back to Eclipse, we can then create another external tools configuration to run JITWatch for us. So we got to run external tools configuration. Create a new one. I'm going to call it run JITWatch. For location, we need Java, so we'll go to Browse File System, and I'm going to use Java 17. select java.exe. For the working directory, we want it to be the project, so we can go to Browse Workspace and select the project. For the arguments, we need to enable the incubating vector API, and then just the normal -jar and the jar file. So basically, we're having Eclipse call java -jar and then the jar file, and then of course we need to also enable that vector API. We can click Apply, Close, and we now have that tool listed here. So I'm going to go ahead and rerun the collect JITWatch log version and let it finish this time so it can collect the complete log. Alright, so we know that it's finished running because the stop button is gone and also it says terminated. So now we have the log file. And also if you right click on the project and go to refresh, we can see the log file and the JITWatch jar. Now we can go ahead and run JITWatch. First thing we need to do is pick the log file. So you go to open log and choose hotspot.log. And this is kind of part of why I put the jar file inside the project folder, is it just makes all the defaults a little bit more convenient. Anyway, so yeah, pick the log file, open, go to config. We need to add the source folder. So we go to add folder, choose source, select folder, add the JDK source, and it will automatically pick it for you. And then we need to add the compiled class folder. That'll be in bin. Go to save. And now finally we can have it start to parse the file. So we click start. And now we have the various packages here. So for my simple demonstration code, it's not inside a package, so it'll be in the default package. You can go to main, and now we can take a look at the code for any of the functions. So for example, if we want to look at the scalar code, we click that. And here we have the code. So on the left side we have the Java source code. In the middle we have the Java bytecode, and on the right we have the actual assembly instructions that are used. Also, if you hover over an instruction, it'll tell you a little bit of information about it. Like in this case, MOV is obviously a move, XOR is a logical exclusive OR, and so on. I found that for some instructions it didn't have a description for. Let's take a look at one of the vector functions. So if we go to vector A, now unfortunately it doesn't have information about a lot of these vector instructions, and it mentions an assembly reference being loaded. I haven't been able to find a way to load any information about the assembly. Another interesting thing is if you look at the Java bytecode, any of the green lines, if you hover over them it'll tell you some more information. So in this case it was inlined, which is useful to know, that kind of thing. Well, it'll give you information on any line you hover over, but the green lines are, kind of curious to look at. Anyway, so we can see here, this was my first attempt at vectorizing the code, where I just copy it into one register, and then I do a reduction operation to sum all of the registers. And we can kind of see here we have a bunch of vector instructions that are kind of leading up to that. So I'm not an expert at Intel assembly, but it's also useful to take a look at Intel's instruction set architecture when you're trying to figure out what is actually happening behind the scenes. So Intel calls it I think they call it the SDM. Yeah, the Architecture's Software Developer Manuals. Yeah, so I'd recommend you download this. It's a big file. It's, I think, several thousand pages. Yeah, almost 5,000 pages. And like if you run across an instruction where you're not sure what it does, so let's say MOVSX. Well, in this case it's pretty obvious, but if you didn't know what it was, you could do Control F, MOVSX, and then you could, find more information on it and all the variants. And before you actually read, or before you start skimming through the document, the first few chapters are particularly helpful. So chapter 2 kind of helps to explain some of the issues and quirks of the instruction set architecture. Anyway, so that's basically the information I wanted to share in this video. I hope it was interesting and helpful, or at least a little bit entertaining. If you have any questions or comments, leave them down below. Obviously, I'm not an expert at vectorizing code, but if I have any ideas or if I have any answers, I'm happy to help. And if not, maybe somebody else can comment. All right. If you know anybody that might benefit from this video, please share a link with them.